root cause analysis, explanations, and causal discovery. This week, we travel to sunny California to hear from researchers who presented their work at this year's edition of the CLeaR conference on causal learning and representation. Enjoy.
I'm Kevin Debeire. I work for the German Aerospace Center in Munich. So my work is about applying causal discovery methods with climate time series. And for this conference, I was presenting a paper in which we used Bootstrap aggregation to provide confidence measures of the edge outputted by time series causal discovery methods. And also we found empirically that the aggregated graph resulting from the Bootstrap aggregation had also higher precision and also recall compared to the baseline method that we tested for the empirical experiments.
What impact would you like to see of your work in the real world?
So for me, I'm really focusing on applications with climate time series, and I would like to see applications of my methods with climate time series in order to understand better climate processes are linked together, so we could understand better how climate change is impacting those processes from climate models, and also we would like to understand if climate models are able to represent these processes correctly in the historical data.
What are the main insights, something that you learned while working on this project?
Good question. I think for me it was my first time working with so many people on the paper, I would say, and so I learned how to write the paper in a group, and all the review process, and that's what I learned, I think.
What should people type in Google in order to find your work?
I think if you type Bootstrap aggregation for time series causal discovery, you will find the archive paper.
What is the best causal paper you read last quarter?
So it's actually a review paper which was written by Gustavo Campfiles from the University of Valencia, and it's presenting all the current methods. And I think the paper is called Discovering Causal Relationships and Equations from Data, and it's explaining the current methods to estimate causal relationships and equations from data, and also presenting opportunities and challenges in this domain. So it's more focused on physical sciences. So for me, it's quite relevant, and I really enjoyed the paper.
Great. Thank you, Kevin. I appreciate it.
Yep.
Hi, my name is Yuchen. I'm a PhD student at UCL.
What is your work about, the work that you're presenting?
Okay, so the work I'm presenting today is called Meaningful Causal Aggregation and Paradoxical Compounding. It's some work I did while interning at Amazon Research Tübingen. This is joint work with Kailash Buddha-Toki, Jonas Göbler, and Dominic Jansing. In this work, we show an interesting paradox we find when we consider aggregated causal models, which is that even the property of confounding, which is a structural property of causal models, even that is well defined when we consider ambiguous interventions on aggregated variables. We make a simple realization, which we call natural intervention, which can help us mitigate this problem. And we also try to generalize this observation to larger graphs.
What would that mean to make an ambiguous intervention?
Yes. So when the variables that we consider are aggregated variables of some fine-grained micro-level variables, then when we intervene on an aggregated variable, there are many different ways of realizing that intervention on the micro level, for which we assume that we do have a robust causal model for.
Could you give an example?
For example, Amazon has millions of products, each of which might have different prices. Then when they want to ask questions such as, if I sell more cleaning products, how would that impact my downstream revenue? Number of cleaning products sold is an aggregated variable. And you might have different cleaning products with slightly different prices. So how exactly do you sell them will have different impacts on your downstream revenue.
What impact of your work would you like to see in the real world?
Because most variables that we care about are aggregated variables, yet there's only limited academic work analyzing how we deal with this, like the consequence of ambiguous interventions. I would definitely like to see this problem being analyzed more for real-world applications. And also, it would be nice if there can be work that can learn from data, a set of macro variables for which is complete in some sense in summarizing this micro model. I think that'll be really useful for real-world applications.
What should people type in Google in order to find your work?
The title works, Meaningful Causal Aggregation and Related Paradoxes, or you can search my name, Google, and it's on my Google Scholar.
What is the best causal paper you read last quarter?
So there is this paper that I always go back to called Multi-Level Cause-Effect Systems. It's written by Christoph Klubka, I think in 2016 or 17. Basically, in this case, it learns these like sufficient macro variables for a specific model. I always go back to it. And I think it's even given me some inspirations for understanding how to mitigate reward hacking, for example, for large models. Because in that case, we also want to think about transfer from some kind of lower dimensional models. I think it's a really nice paper.
Great. Thank you so much.
I'm Konstantin Göbler. I'm from Germany. I'm a fourth-year PhD student at the Technical University of Munich. I'm with Matthias Dutten's group there. And since 2 years, I'm also affiliated with the Robert Bosch GmbH. And we do a bunch of stuff with them together, I guess.
The work you presented here, what is it about?
So the work that I presented is, I call this causal assembly, or we call this causal assembly, and it's basically aimed at facilitating benchmarking causal discovery algorithms. So it's more or less like a service for the community, but also I think it's filling a gap of in the field. There's some issues of attaining reasonably complex ground truth data for causal discovery. So we managed to convince the people at Bosch to make public access, not really public, but we tried to manage to find out a tool that makes proprietary data publicly accessible via some semi-synthetic data steps. We do so in a somewhat principled manner with a bunch of steps in the middle so that people are assured to, when they benchmark their causal discovery algorithms with this library that is implemented in Python, that the data really follows the ground truth causal graph that is also implemented in there.
What is the advantage of your approach compared to other approaches that are available in Python today?
I think the advantage is that we almost should do this basically for any implementation. I think that is where people are somewhat uncertain about the ground truth causal structure that is given to somewhat complex real data, I think. Because as soon as there's some uncertainty and you run your favorite causal discovery algorithm on this data, like the worst case scenario is that your algorithm is correct, but you think it's wrong because your ground truth is wrong. So what we basically do is we make sure that the data that you run your causal discovery algorithm on really follows the ground truth that is at hand.
What impact of your work would you like to see in the real world?
That's a hard one. I think so. The impact of my work ideally is that it, like I said, it facilitates progress in the field such that causal discovery is more reliable and is able to scale better such that real-world problems can be solved to a certain degree.
What should people type in Google in order to find your work?
Causal assembly.
What's the best causal paper you read last quarter?
So it's not necessarily, I think, a strict causal paper, but I really, I dived a little bit into ICA and there was a paper on nonlinear ICA that I very much enjoyed. The paper itself is very readable, but the proof is very hard. So I very much enjoyed the nonlinear ICA by Ignavier. and a couple of co-authors, I think. Yeah.
And do you remember the author of the title?
So I know that the second author is Ignavier, who was also awarded the best paper here.
Thank you so much.
Thank you.
Hi everyone, I'm Urja Pawar. I am from Munster Technological University Cork in Ireland, and my PhD is funded by Science Foundation Ireland and McKesson Private Limited. I am presenting the impact of neighborhood on explainable AI frameworks, such that I want to know how much they are able to convey the sufficiency and necessity of features. So sufficiency and necessity are the fundamental, blocks of any explanation. We don't want to know which feature is sufficient in maintaining the classification as it is, and which feature is very, very necessary that if the feature values get changed, then the classification will get changed. So there are these sufficiency and necessary concepts. Now, we do have many frameworks in explainable AI, especially state-of-the-art frameworks like Sharp, Line, DICE. DICE is a counterfactual library. And we extracted feature importance scores using that libraries, and we wanted to see how much these feature importance scores are able to convey the sufficiency and necessity of features. The reason why I was doing that is because if you are provided with a feature importance ranking, you can interpret it in very, very different ways. I can say that, A is very, very important. So if I change the value of A, the classification might change. If somebody else is reading that feature importance ranking, he or she, let's say a clinician is reading it, and he looks at the feature ranking and it's like, this test is not given that much importance by a machine learning model, so it might not be very important as per the model. So go train your model again because this test is very important. So there can be different interpretation, and we don't know what to interpret from that ranking, right? So that's why we developed this concept called Explainendum. We define it properly and we try to see what exactly to interpret from that ranking that we are getting provided. So I focus on the basic fundamental blocks, Explainendum, which is sufficiency and necessity. I wanted to know if I'm looking at the topmost ranked feature by Sharp, am I gonna get conveyed that this feature is the most sufficient feature or the most necessary feature, and so on. Now the problem is these frameworks are very, very sensitive to the neighborhoods that they use for explaining. And different neighborhoods can produce different explanations. Sometimes, you can always innocently use certain samples in the neighborhood and it can produce very, very false explanations. We tried a range of neighborhoods to see how much each of the neighborhoods can help these frameworks to convey the sufficiency and necessity. And we wanted to identify the best neighborhood that can help, let's say, Sharp to convey the sufficiency of features. The outside-based neighborhoods basically perform well, which means that if I'm focusing on samples that are outside the decision boundary, Sharp can help me in producing a ranking that can tell me, look, this is the most sufficient, less sufficient, and so on. Same with necessity of features. But the high level takeaway I will say from my paper is that people should draft a specific explainendum and then try to see whether these frameworks are able to convey that explainendum or not. And if not, then experiment with different neighborhoods and try to find your answers, which neighborhood is giving you the most relatable or relevant answer to answer your own explainendum. So yeah, that was pretty much my research.
Yeah. Right. Does this conclusion mean that it's very difficult to just find one framework that would universally work and be reliable at the same time?
Yeah, so we have loads of papers that talk about there is no free lunch theorem in explainable AI as well. The main thing is that you need to be clear of your explanatory requirements here. If I am a clinician, I am some stakeholder in any finance company where loads of machine learning models are getting used, without defining specifically what to interpret from the explanation that I'm provided, anything is very, very ambiguous and it's very useless, because now it becomes a checkbox exercise that, okay, you are providing me explanation, good, I trust your model, and that's it. What is that explanation doing? Is it helping you? Is it really representing the model truly in all ways? So I think multiple explainable AI frameworks using different neighborhood contexts is important to understand the whole actual truer picture of a model, basically.
But what impact of this work would you like to see in the real world?
I actually had a chat with nephrologists in Galway University Hospital back in Ireland, and I wanted to talk to them about I developed a more complex explainendum in medical domain, which basically meant if I'm looking at the feature importance ranking, can I say, okay, I don't need to do further tests. As per machine learning model, I don't need to do further tests. Or can I also answer another question, which is, as per the machine learning model, which is the next most important diagnostic test that I would like to do? So these are the questions that we wanted to answer using the same methodology that we adopted in this paper. And we discussed this with the clinicians, and they really liked our work. So I really want to see more and more truer forms of explanations with clearly well-defined explanandum, so that people don't follow all this as a checkbox exercise for ethical permissions and all, and actually present the true picture of the model to the stakeholders, basically.
What's the best causal paper you read last quarter?
I have not read a causal. I don't remember if I read a causal paper, because my domain, I really focus on explainability. I do think, of course, my domain should be very, very overlapping with causality, because without causality, it's kind of ambiguous to have explainability. And we did work on causal relationship in a way that we constructed medical workflows, like which test comes after what test and everything. I think in the last quarter, my favorite paper that I can share is Dear XAI community. It's a paper that you can just write the Dear XAI community, and that paper talks about how much here and there the research is going on in explainability. People are not standardizing the concepts. People are not focusing on one single definitions of things. Defining and also the importance of explanandum is highlighted in that paper, that you need to be very clear of who is your audience, what are you exactly trying to explain, and what action someone can take looking at your explanation. So I think these are the questions that are the whole point of our domain, and people should work more and more on that rather than just developing novel XAI frameworks to create just another ranking without defining what to get from that ranking. So, yeah.
Thank you so much.
Thank you so much.
Hi, I'm Will Orchard. I'm at the University of Cambridge, but the work I did here, I did at Amazon as an intern in Tübingen. My work is about root cause analysis from a number of directions. One is how root cause analysis should be formalized as a causal problem. And two is the real-world application of root cause analysis to real-world problems, such as in microservice-based applications at Amazon.
Can you say a little bit about your approach?
The approach to formalizing root cause analysis, essentially there's a lot of existing works on root cause analysis, and each of them have typically approached it not from a causal perspective, despite the fact that the cause is in the name. One thing I've done is I've just gone through a lot of works and tried to figure out whether there is a unifying causal description you can give to each of these methods. And at the moment, there isn't very much literature on how root cause analysis methods should be classified, but sort of unsurprisingly, you can classify them according to the causal hierarchy about the way in which they think of what a root cause is, whether or not it's an associational question, an interventional question, or a counterfactual question. And so my approach has been to just try to classify what already exists. And then in particular, because I've worked with Dominic Janssing, he's very interested in the counterfactual approach. So in a counterfactual contribution approach to root cause analysis would be.
What were the main challenges in this work?
Yes, that's a good question. So I think there's a number of things. So one is a question which comes up when you're trying to formalize any problem, right? Which is, what is the best way to ask a question which sort of captures your intuition about how a problem should be formalized, right? Whether or not it truly captures the thing that you're trying for it to capture, right? And I think causality can give very convincing answers to whether or not you're giving a good explanations for something like a root cause. And so just trying to get my head around about whether or not we were asking the right question and how other approaches were asking this question and what the relative merits were of each of those things. That was challenging just on a sort of conceptual level. And then sort of relatedly, the question was whether or not this formalization actually works in real life for real problems. Yes. And that involves obviously talking to engineers and people like this who work with this data and have sort of developed their own heuristics and things like this for solving this problem, and whether or not this formalization captures their experience as well.
Sure.
Yeah.
What are the main learnings, main insights that you got from this work personally?
I think the first thing I learned was I think the question of what is a root cause is actually a very deep question. I think it's interrelated to lots of questions in causality about Explainability is totally related to questions of sufficiency and necessity. It's also closely related to the relationship between anomalous values or rare values and interventions and things like this. So I really think I learned a lot about causality from this perspective, and root cause analysis I think really is connected to lots of these things. I also learned that engineers typically aren't very interested and it really requires some convincing to tell them that this stuff is important and that it can help them out. So that was very interesting.
What impact of your work would you like to see in the real world?
I think the first thing, particularly with this work, is there really has been almost a total lack of standardized data sets available for evaluating root cause analysis methods. And I think one of the impacts of this has been very many methods being developed not from a causal perspective, which aren't being benchmarked against many other methods. So like each new paper has its own way of evaluating the approach, typically with simulated data, and then they don't release the data publicly, and it becomes very unclear as to the way in which you formalize the problem is seen in benchmarking results, right? So having publicly accessible data sets, I think, is really important actually for trying to convince people that causal approaches are important, and also to actually understand which ways of understanding this problem work in practice. I really hope that people are going to use this data set, learn more about root cause analysis, and we can come to some kind of consensus about the best way to approach it. So,
where can people find out more about you and your work?
I think mainly my Twitter. My Twitter is where I usually post information about my work. In this case, this paper is available on arXiv. The dataset is available on a Git repo, and there are QR codes in the corner here. And then I, of course, also have a Google Scholar. But yeah, those are the places to go.
What should we type in Google to find the dataset?
Yeah, pet shop datasets, Amazon, that kind of thing. Yeah.
What is the best causal paper you read last quarter?
Yes, this is a very good question. So I think one paper I found quite inspiring recently is causal discovery methods. So this is somewhat unrelated to root cause analysis, but these score-based causal discovery methods, which are using the score in terms of the derivative of the log of the probability, right, of the data. And so there's this score algorithm, there's this no GAN method, and I think there's sort of the theoretical work which has gone into the identifiability results for this sort of thing, and the way of using score matching to do causal discovery, I found really exciting. It's just, I think, some of the best causal discovery work I've seen in a long time. So yeah, that's been great. And then also this work from Jonas Peters on using heavy tail distributions for causal discovery and identifiability there. That also comes to mind. I think this is related to root cause analysis. So yeah.